Hello, in this video I want to share with you two ideas on the problem of irreversibility. So one of the fundamental problems of statistical mechanics, and the two ideas are related with Boltzmann's explanation of irreversibility. Irreversibility is usually illustrated with videos like this one. Here we have two gases, one with the molecules in blue and here in red, and they are separated by a wall. And you can see also that the blue one is a bit hotter than the red one. If we remove the wall, there is a mixture of the two gases, and this is an irreversible process. It's impossible to observe the reverse process, that is the segregation, the spontaneous segregation of the molecules into two gases with blue and red molecules. But if we zoom in, what we see is just elastic collisions following Newton's dynamics, which is completely reversible, and we don't see any signature of an arrow of time or irreversibility. So from this video, one gets the impression that irreversibility is something that has to do with macroscopic systems and with the macro scale, whereas the microscopic dynamics is completely irreversible. I will show you that this is not completely correct. Boltzmann explanation is well known. It's based on the analysis of the microscopic dynamics of the system. He first studied the phase space. We call the phase space the set of all the microstates of the system. So here is a cartoon of this phase space taken from a book by Roger Penrose, and each point here is a microstate, which is a detailed description of my system, in this case the two gases. So it would be, in this case, the position and the velocity of all the molecules in the system. Of course, this is a very complicated space. It's a high-dimensional space. If the gas has 10 to 20 particles, 10 to 20 molecules, as usual, in a macroscopic volume, the phase space is a space with 10 to the 20 dimensions. So it's a very complicated set or space. And each point here, it contains the information of all the positions and velocity of the molecules. On top of that, you can imagine that when we let the system evolve, like in the video, in the phase space, the system will will follow a trajectory, a microscopic trajectory, and this trajectory will be also crazy, will be very very complicated. Suppose that here every maybe nanosecond there are millions of collisions, and in each collision the velocities change abruptly. So this will be reflected in this trajectory. So Boltzmann realized that these microstates and this trajectory are not accessible to a macroscopic observer. So he introduced the concept of a macrostate. A macrostate is the state that a macroscopic observer like us would see. And of course, a macroscopic observer cannot distinguish between this microstate and maybe the same macrostate with this molecule a little bit up or down. So the observer has only access to macroscopic variables, that the global density and so on, and the pressure and the temperature and so on. So for this macroscopic observer, a macrostate is a set of microstates which are compatible with this macrostate, like this region here. So each macrostate is a region in the phase space. And the second discovery by Boltzmann was to realize that for typical macrostates, the volumes that these macrostates occupy in the phase space, they are disparate. There is a single macrostate which occupies almost all the volume available in the phase space, and the rest occupy very tiny volumes here and there. So the consequence of these very large differences between volumes of macrostates in the phase space is what induces irreversibility. If the phase space is sampled, the system samples the phase space in a uniform way, then the most likely state will be here. So if the system starts in one of these macro states with a low volume, then immediately just due to probability and this uniform sampling, it will go to macro states which with a higher volume, and finally it will end here. So we will see this trajectory and the reverse trajectory, so that the system starts in this big macro state and by chance it will end in one of these macro states which occupy a low volume. This is very unlikely, so we will see a completely irreversible behavior. This is Boltzmann's explanation. This was formulated by Boltzmann in the end of 19th century. Some people was not completely convinced, and there is a famous paper by Joel Lebowitz in Physics Today in 93, which was also very influential, because what Lebowitz did with this paper is to claim that Boltzmann solved the problem of irreversibility, so there is no need of any further explanation. He says that given the success of Ludwig Boltzmann's statistical approach in explaining the observed irreversible behavior of macroscopic systems, it is quite surprising that there is still so much confusion about the problem of irreversibility. And it's true that very relevant researchers like Prigogine, they thought that there should be something else. There should be some irreversibility in the microscopic dynamics or some further explanation. So they were not completely satisfied by Boltzmann explanation. Lebowitz goes on and he says, I see no need for alternate explanation. So he claimed that Boltzmann solved the problem of irreversibility in a completely satisfactory way. It's true that he further on in the paper admits that there is something which is precisely what I want to address, this objectivity of Boltzmann's explanation. He admits, Lebowitz admits, that there is some arbitrariness in the definition of a macroscopic state. So far, I define a macroscopic state as the state that the macroscopic observer can have access to. But what is a macro state? Lebowitz says this arbitrariness or subjectivity, I will use arbitrariness and subjectivity as synonyms. He says that should not concern us too much, since all the statements made by Boltzmann are independent of the precise definition, as long as there is a large separation between the macro and the micro scale. But this arbitrariness does concern me because, because first we have all this nanotechnology and the manipulation of microscopic systems, and it's not clear what is now a macroscopic observer, or does the macroscopicity of an observer depend on the technology that we have available? And even though we could define macro and micro scale, what is the crossover between these two scales? So these are problems that I think in the original explanation by Boltzmann and in Lebovitz's paper were not completely solved, or were not solved in a satisfactory way. So my idea here is to answer this question: can we define macrostates in an objective way, or can we explain irreversibility in an objective way? And the answer is yes. If we, instead of trying to explain the increase of entropy or the arrow of time as increase of entropy in a system, we can solve the problem of objectivity, of irreversibility, if we reformulate Boltzmann's explanation of irreversibility using observables. And this is a very tiny change in the Boltzmann explanation actually is something that it is implicit in other, even in some textbooks, but I think it has not been formulated precisely, and this is the purpose of this video. And in the second part of this video, I will show you that one of the problems of Boltzmann explanation is also the initial condition, how we can have in this irreversible behavior, how can we achieve an initial condition which is completely impossible to observe in a spontaneous way. And I will show you that a mechanism to create giant fluctuations in physical systems. So let's go first to the first part, which is an objective reformulation of Boltzmann explanation. Boltzmann explanation is the one that I've given before. Let me be a little bit more quantitative. Boltzmann was able not even to explain irreversibility in the terms that I've shown you before, but also he was able to relate entropy of a macrostate with these volumes in phase space, the volume of the compatible microstates, the microstates compatible with the volume of the microstates compatible with this given macrostate. And this relationship is the famous Boltzmann formula, which is in his grave and involves the Boltzmann constant. Okay, so the idea is to focus on a slight modification of Boltzmann explanation and define entropy, but for observables instead of the entropy of a system or the entropy of a macrostate. So in classical mechanics, an observable is just a property of my system. If my observable takes on real values, it's just a function from the microstate, that is from the phase space, to the real numbers. So to each microstate assigns a real number, which is the value of this observable in this microstate. This can be the total energy of the system, it can be the position of a single molecule, the density in a given region, the velocity or the kinetic energy of one particle or a set of particles. Any observable that you can imagine can be represented by a function. So we can use Boltzmann idea, but for observables, which is to define the volume in phase space, in this case is omega, the volume of all the microstates x, which are compatible with a given energy, and also with a given value, small a, of my observable. So this is this definition. We can use delta functions to express an integral that only calculates the volume in phase space, gamma, which is compatible with a given value of my observable and a given energy. This is called omega AE. And we can define an entropy function now associated with my observable, capital A. So I have an entropy, which is an entropy that depends on the possible values of my observable, small a, and on the energy. And if we now invoke this ergodicity property or uniform sampling of the phase space, we can derive this formula. If the system is exploring the phase space in a uniform way, the probability that my observable, capital A, takes on a value small a is given by the fraction of volume in phase space compatible with this value. Or if you like, using Laplace old formula, the number of favorable cases divided by the number of total cases. And this is the probability to find that my observable capital A takes on a value small a. If we use now the expression for the entropy, this is proportional to the exponential of the entropy divided by Boltzmann constant. And this is an old result which is known in some textbooks as the Einstein's formula, because Einstein used this formula before 1905 to study fluctuations in statistical mechanics. What is the meaning of this probability? Well, it has a completely objective meaning. If you run the experiment for a sufficiently long time and you register the values of A, you will see an evolution like that. And now if you plot the histogram of these values, you will get this rho A that we have derived before. And this is because the system is exploring the phase space in a uniform way. So this probability distribution will have a maximum. This is, if you like, the most likely value of my observable. And this most likely value, if you go to the expression of the probability, is the value that maximizes the entropy. This is just Boltzmann explanation, but replacing the notion of macro state by the foliation that my observable A creates in the phase space. And the difference is also that this observable can be anything. Can be microscopic or macroscopic. Can be the position of a particle, for instance, or can be the local density in a big part of my system, which would be macroscopic. If the observable is macroscopic, we know that following Boltzmann, that this probability distribution will be almost a delta function, will be highly peaked around this value. So almost with probability 1, my observable will go to A star, to this most likely value, and will remain here for a long time, except for tiny fluctuations. But I want to stress that you can define this for any observable. For any observable, you can define this, and you can define also this rho A, microscopic or macroscopic. Of course, to have this uniformly sampling of the phase space, you need that the system must be macroscopic or must have a large number of degrees of freedom. Otherwise, you will have periodic orbits and so on. So we need a macroscopic system, but this definition and this definition of entropy and this result is valid for any observable. And this is the key point of my argument, that you can define entropy for any observable, and you can obtain irreversible behavior in any observable. If my initial condition is very unlikely, and this is equivalent to this condition, if the entropy of my initial condition is much smaller in units of Boltzmann's constant than the most likely entropy, so I'm here, this means that immediately the system will go to the values with a non-negligible probability. So we will see irreversible behavior. We will see that my observable goes immediately to this most likely value or values around this most likely value. Okay, and this is fully objective. This is the point. This is fully objective. This condition, the definition of entropy is the one that I gave in the previous transparency, and this is the mathematical condition. And if I have an initial condition like that, obeying this inequality, then I will observe irreversible behavior. And this does not depend on the scale or on the observer, or nothing to do with some arbitrary choice of the observable. So this shows that some observables probably will have irreversible behavior, some will not, but there is nothing arbitrary or subjective in this definition. Of course, it's not a precise definition. So we have to distinguish between definition of a concept or the characterization of some behavior when it's objective. Objective means that does not depend on any choice of our arbitrary choice or the properties of an observer or something like that. Precise means that there is a precise separation between one behavior, let's say reversible and irreversible. We know that this is impossible. We know that there is not a clean separation between irreversibility and reversibility, because we always have in the microscopic world and also in the macro, but they are very small, we have fluctuations, and that any irreversible behavior is going to be masked by fluctuations. One can observe fluctuations where the entropy goes down by values of the order of the Boltzmann constant. So we knew that it is impossible to explain irreversibility in a very precise way, like to conclude that some property will have a irreversible behavior and this will not have an irreversible behavior, because the irreversibility is always going to be masked by these fluctuations. But don't mix objectiveness and preciseness, which are two different concepts. And I insist this is a completely objective definition of irreversibility. And it's not so, I mean, it's just like a footnote in Boltzmann explanation. No, instead of using macrostate, we use this observable-dependent entropy, and we can characterize reversibility for observables instead for a system in general. But if you adopt this new way of seeing Boltzmann argument, you really understand better what is the meaning of irreversibility. And I will show you in two examples. I will show you precisely that in a system you can have observables. Some observables could have an irreversible behavior and some others will not. And this has nothing to do with the scale of these observables. So let me illustrate this idea with two examples. The first one is the position of a molecule in a gas. So suppose you have a gas in a box, and this is the coordinate x, and you consider the following observable, the position of a single molecule, of one molecule, let's say molecule 1, in the x coordinate of this molecule. Well, it's a very simple calculation to show that the entropy, as defined in my previous slides, is constant. So if it is constant, you can never have a value. This is always constant, this is constant, so this is 0. So you can never reach this condition for irreversibility. Or in other terms, the position of a particle can never exhibit an irreversible behavior. You see that this condition, to be fulfilled, needs that the range of my observable must be much bigger than the fluctuations, the typical fluctuations of my observable. So here it's impossible because the range of the observable x is the whole box, and the fluctuations of x are also the whole box. It's worth it to mention that this condition, the condition that I've mentioned, that the range of fluctuations must be much smaller than the range of the observable, is the same one that Riemann and Gemmer require for typicality for some properties of typicality in quantum systems. This is the first example of an observable that can never exhibit irreversibility and is microscopic. But this does not mean that all microscopic observables couldn't exhibit irreversibility. Suppose now the velocity of a molecule, let's say the modulus of the velocity. You can calculate the entropy with the formulas that I gave, and this is the result, where T is the temperature of the gas and m is the mass of the molecules. If you apply Einstein formula, remember that rho of b, the probability density of the velocity, is the exponential of this, you get the Maxwell distribution of velocity. So there is nothing new here. And the most likely value is one that it's around, the one that gives you a kinetic energy of order kT. And this observable, the velocity of a single particle, of course, has the probability density is broad. So you have big fluctuations. The fluctuations are of the same order as the mean value. So, but even though we can have an irreversible behavior, if this is Maxwell distribution, we can start for some reason with a very high velocity, and we will observe irreversibility. So the condition is this one, that the kinetic energy is much larger than kT. And this can happen. You can imagine that maybe you have a gas in equilibrium, and suddenly a particle coming from a supernova or whatever with a lot of energy collides with one of your molecules, and this molecule, for this reason, acquires a kinetic energy which is 100 kT, for instance. The probability that this occurs spontaneously without the collision, spontaneously in the evolution of the gas, is the exponential of minus 100. Even if you have 10 to the 20 molecules and you ask for the probability that one, no matter which one, acquires this velocity, this kinetic energy, 100 kT, this is zero. The probability of observing this as a spontaneous fluctuation is zero. And here we are even asking for a given molecule. So this molecule acquires suddenly a velocity 100 kT. Well, this velocity will exhibit irreversibility. If an observer measures the velocity of these molecules, she will see that from 100 kT, immediately the molecule, after a couple of collisions or after several collisions, will go down to velocities which are of order, or to kinetic energy which are of order kT. So if you start here, you will see an irreversible relaxation, exactly as the ones that you see in macroscopic systems, except that the macroscopic system goes to the equilibrium value, which maximizes entropy. And here we go from this very unlikely value to values which are likely and which are around this V star here. But it is an irreversible relaxation. And look at this. We have for a macroscopic observer, the observer that Boltzmann had in mind, the gas is in equilibrium. The macroscopic observer cannot observe any irreversibility in the system. It's the microscopic observer, the one who is looking at the velocity of a single molecule, is the one who really sees an arrow of time, which is present in the system. So this example tells you that irreversibility has nothing to do with the scale. You can have irreversibility in the micro scale and reversibility in the macro scale. So it has to do with fluctuations. So if my initial condition is a very rare fluctuation, the value of my observable will go back to typical fluctuations. And that's it. It's as simple as that. Okay. So to finish this first part, we could be tempted to try to define equilibrium for microstates. We could say a system is in equilibrium if there are no observables with an irreversible behavior. In other words, we could say a microstate is equilibrium if for all the possible observables, the value that these observables take on in my microstates are typical fluctuations. This is nice, but it doesn't work. And the reason is that for a given microstate, x0, I can always define this observable, the observable that takes on the value 1 in this macrostate and 0 otherwise. The entropy, now the entropy function will be, the entropy of 1 is 0 or minus infinity, because this volume is just 1 point. And the entropy at 0 will be the volume of the whole phase space. So this observable will always have an irreversible behavior if the initial condition is, if the state is x0. So this observable will always exhibit irreversibility like that if my macro state is x0. So this definition doesn't work, I think, maybe by restricting in the definition the set of observables. One could maybe get a definition for equilibrium which could be objective. So the open question that I have here is that maybe if we restrict the set of observables, the restriction must be objective. So must not depend on the observer or cannot depend on the scale or things like that. So if we can restrict the observables to some objective family of observables, then maybe we can get an objective definition of equilibrium for microstates. And this is probably related with the work in quantum typicality for quantum systems. Okay, yes, this is the end of the first part of my talk. For the conclusions, I want to say that I think that more than reformulating Boltzmann explanation in an objective way, I think that what I told you clarifies what are the objective ingredients and subjective ingredients in the typical Boltzmann explanation, or even in the statistical mechanics that we use every day. So if you define entropy for an observable, this is fully objective. It's just a formula. It's the volume in phase space. The entropy function is k log omega, and omega is these integrals that I've shown you at the beginning of the talk. The irreversible behavior is also completely objective. So some observables exhibit irreversibility and some others don't. And this is completely objective. It's not precise because it is always masked by these fluctuations. And the second law is also, for a given observables, is also objective. So if once we define the entropy function, we know that the entropy increases, and this increases up to fluctuations of order k. So, but if I start with an entropy which is 100k times the maximum entropy, I know for sure that this will go up to entropies which are of order of the maximum entropy, and with fluctuations of order k, fluctuations that we have observed in many experiments, so this is nothing new. And this is fully objective. Where we start to have arbitrary choices or subjective choices, well, when we choose the observables. When we say that, well, in this system, I'm going to choose this, the pressure or the volume, the density, etc. One example, which is the typical one that we use in stochastic thermodynamics and in the situations that we study in stochastic thermodynamics, is you have a system surrounded by a bath. And not only in stochastic thermodynamics, but in biophysics, in the study of Brownian motion, in many experiments with the Brownian particles and so on. And it's a choice that it is induced by how we treat this problem. And when we have a system in contact with the thermal bath, usually we take as observables the microstate of the system, and we say that the observer has no access to the details of the bath. So it has access only to the average energy of the bath or the temperature. And then when we have this choice, we can derive formulas for the entropy production using Clausius expression and so on. So in this case, let's say that the physical scenario imposes somehow the choice of observables in a kind of objective way, although the separation of what is the system and what is the bath is not always a kind of, it's not always something 100% objective. And also the entropy of a system, because the entropy of a system, we have defined the entropy of an observable, but the entropy of a system is also something that you can define if you choose some observables. as in Boltzmann explanation, he uses the concept of a macro state, but you have to choose what is the macro state, and this is an arbitrary choice. And in between, I let the notion of equilibrium, because as I said in my previous slide, I'm not sure if we can define in a completely objective way the concept of equilibrium. Okay, now let's go to the second part. The second part is again about the Boltzmann explanation, in the sense that Boltzmann, or the new formulation that I've shown you before, because to have irreversibility you need a very unlikely initial condition. You need an initial condition with a completely negligible probability, what I call a giant fluctuation. So you have the typical fluctuations of my observable, and to observe irreversibility, you need a giant fluctuation, like the one in the gas that I've shown you in the first video. You need the blue molecules here and the red molecules here, and you need somebody to prepare this. This cannot be the system cannot achieve this state spontaneously. So how in nature systems can take on, or some observables can take on these values, which by definition are not achievable by a fluctuation. This can be considered a fluctuation, a giant fluctuation, because if we run a simulation, for instance, of this system, and we run the simulation for negative times, we will get also irreversibility irreversibility. We will get also that the system goes to the most likely values, or to typical fluctuations. But this is a giant fluctuation, and the probability to observe this is almost zero. So to achieve this value, we need a preparation of the system, or some mechanism that creates this or some mechanisms that generates these giant fluctuations. The conventional answer to this problem is that the universe started in a very low entropy state. After the Big Bang, the entropy of the universe is very low, and somehow this very low entropy is transferred to planets and to the sun, and then the sun creates a non-equilibrium environment in the Earth, and the Earth can develop the life because of these non-equilibrium properties, and so on. So it is every low entropy state like this one is the result of this very low entropy at the beginning of the universe. But I think this is not completely satisfactory, because it is not clear what is the mechanism to transfer the low entropy in the, let's say, state of the universe to the low entropy of local systems like the Earth or the Sun and so on. And the question is even harder if we think of the phase space of the universe. Like, okay, we are in a very small region of this huge phase space, but then how local systems, like my gases in the laboratory or like the sun, can also go to very tiny regions in their respective phase spaces. So this is something that I think it needs an explanation. And the explanation that I propose is very simple. It's based on metastable states. So let me explain how a giant fluctuation can be originated when a system undergoes symmetry breaking, phase transition, or ergodicity breaking. So, for instance, suppose that I have a gas in the gravity field in the Earth. So the gas is in a box, and here there is a kind of shelf. So I have my gas, and if I cool down the gas below the condensation point, the gas starts to form drops. And you can have a drop here on the top of the shelf, or you can have a drop here at the bottom of the box. And the probability that the drop forms here or here is almost the same. We see it in the bathroom, that we can have drops formed everywhere. But if you look at the entropy, so at the size in phase space, the volume in phase space, and the log of this volume, which is the entropy of this drop is much lower than the entropy of this one. The difference of the entropy of this drop and this drop is the amount of energy dissipated to the environment, which is mgh. M is the mass of the drop, and h is this height. And if you divide this by temperature, you get the entropy. So the entropy in units of K is given by this expression. And if you put, let's say, normal numbers of a drop of 1 gram and 10 centimeters and room temperature, you get 10 to the 17. Which means that if you go now to the phase space, the volume in phase space, the volume of this configuration of the drop here is the exponential of 10 to 17 times larger than the volume here. So it's a crazy number, exponential of 10 to 17. If the phase space were sampled uniformly, the probability that the system forms the drop here would be exponential of minus 10 to 17. So, of course, the ergodicity property breaks down here. I mean, because the probability that the drops from here is maybe 1/2, if you think of the first drop, let's say. So the probability that it forms here is 1/2, it's a little bit smaller than 1/2. But if you explore, if the system explores the phase space in a uniform way, the probability that the drop is from here is exponential of minus 10 to 17. So, of course, the mechanism here, when the drop is from here, is a huge, not giant fluctuation, it's a super giant fluctuation has been originated by forming the drop here. And this is what in thermodynamics is called a metastable state. Once the drop is from here, we can have a completely reversible behavior by, for instance, letting the drop fall from the shelf to the bottom. Okay, so just to explore this idea a little bit more in a simpler system, let me go to the next example, because here you can say, this is a system that it's being cooled down, so you need to contact the system with several thermal baths, with lower and lower temperature and so on. We can mimic this with an adiabatic expansion. So let me introduce this toy model for the creation of these metastable states or giant fluctuations. So I have a Brownian particle in a gas, and the gas is confined in a volume within one dimension of length L, and I perform an adiabatic expansion. So I move the leftmost wall to the left, like indicated by this arrow. And by doing this, the adiabatic expansion, this means that the temperature will decrease. So I can start with a hot gas, and with this adiabatic expansion, I can cool down the gas. This is not an innocent example, because it is inspired also by the adiabatic expansion of the universe. You know that the cosmic background radiation, now it's at 3 Kelvin, it used to be at 3000 Kelvin. It has been cooled down by an adiabatic expansion of the universe. Don't ask me where this energy goes out. In some books, it says that the expansion, because in the expansion of a gas, the energy is lost. No, the gas loses energy because it is performing a work. The wall is performing a work against the surroundings of the box. But here, don't ask me where this energy goes, because in some books it says that the expansion of the universe requires some energy. In some books I've read that it goes to the gravitational energy of the universe, but in other books I've read that it is not clear what is the total energy of the universe. But what it is clear is that this model of an adiabatic expansion of the photon, the gas of photons of the cosmic background, is very accurate. So it can predict in a very accurate way the temperature of the current temperature of the universe. So this toy model is somehow inspired by this idea that there is a gas which is cooling down because of an adiabatic expansion. Instead of the aggregation of the drops, or in the universe, I think is the equivalent is the aggregation of gravitational aggregates like planets and stars and so on. Here I have just two wells. One is deeper than the other, and this is the depth of the first one is E1, and the depth of the second one is E1 plus delta E. So I will assume that I start with a very hot temperature, so the much bigger than this energy. So KT at the beginning of the process is much bigger than the well. So the particle doesn't see any wells. And after the expansion, the temperature is much lower than this well. So we go from a situation where the particle is in a box without wells to a situation where the particle gets trapped in this well. And of course, because the well is here and we are in 1D, the probability to get trapped in this well is almost 1. It's very unlikely. Well, maybe in the expansion, if the particle is here, it will get trapped here, but it is much the probability that it gets trapped in the shallower well is much larger. So the particle will get trapped here almost in all locations. Okay, now in this example, in this toy example, you can calculate the entropy as in the definition that I gave in the first part of the talk. Now this is the volume of in the phase space of system with energy E. This is the volume in the phase space of macrostates with energy E, and where the Brownian particle is in a given position, x part. And one can calculate this. This is not very hard because the phase space compatible with these two values, with energy E and with a given position of the particle, is a hypersphere. It's a hypersphere of radius given by that. So you calculate the entropy as the log of this. Sorry, there should be a K, Boltzmann constant here. And if you plot it, you get something like that. And this difference is delta E divided by KT. And this can be 100. Let's say we can put here 100. And then if this is 100, this means that the phase space, the volume of the phase space compatible with this, the particle here, is exponential of 100 times highly larger than the phase space compatible with the particle in this position. So if we are in the same situation as before with the drops, if the phase space were sampled uniformly, the probability to be trapped by this well would be e to 100 times larger than the probability to get trapped here. Or in other words, the probability to get trapped here is 0. If the phase space is sampled uniformly. But of course, in my process, the probability of getting trapped in this well is almost 1. So what is going on here? How this huge set in my phase space can be ignored and how the system can go to this, which is much smaller. Well, I try to represent this with this movie. Let me explain what is each. This is a kind of cartoon of the phase space. As I said, for a given position of the particle, the set of microstates compatible with this position is a hypersphere in a space with a huge number of dimensions. So when the temperature is high, all the hyperspheres have the same radius. So this is a cylinder, and its section would be a hypersphere in a very large dimension space. And when I start to perform the expansion, the radius decreases. But if the particle is here, so the hypersphere compatible with this position of my particle and with this position of my particle starts to grow. And the final state is this one. This circle, let's say, is a hypersphere of very large radius. And this is a hypersphere of very large radius. The volume of this hypersphere is exponential of 100 times the volume of this one. So if the phase space were sampled in a uniform way, the particle would be here with probability 1. But because this is a process where the particle is mostly here, and when the gas is cooled down, the particle gets trapped here, this is a volume which is so high that the particle gets trapped here, and it's impossible to escape from that. This is a kind of microcanonical view. In a canonical view, it would be much easier. You get trapped here, and you need a fluctuation of order kt, and if E1 divided by k is much larger than at, it's impossible that the particle leaves this well because of fluctuations. In the microcanonical description, which is the phase space description, is a bit harder to imagine. But the idea is that that once you get trapped here, you can escape. You can never escape from here. So it doesn't matter what is the state of maximum entropy. It's because you have broken ergodicity, and means that even though the position which maximizes the entropy is here and occupies almost all the phase space of the system, the particle gets trapped here because this is also big, although it's exponential of 100 times smaller than this one, but still it's enough to trap the particle here and to create this metastable state and to create this giant fluctuation. Okay, this is my view of how these giant fluctuations can be created. Of course, in the universe would be that the radiation cools down, and then gravitational aggregates can be created, and this is the idea of how these very giant fluctuations of very low entropy states can be created in the universe. It would be, my example has two wells, so it's a symmetry breaking, but with this discrete symmetry breaking. I think continuous symmetry breaking is also interesting as a way of creating giant fluctuations and also slow degrees of freedom. It's a bit like the example, let me explain with this example, which is a bit like the creation of the drops before, but without the shelf here. So you have a gas, and then you go to below condensation points, and you start to create drops here, or a crystal if you like, if you go to solid gas phase transition. And look what happens if you plot the behavior of the center of mass of the whole system. Here is the center of mass of an ideal gas, which is in the middle with very small fluctuations, fluctuations of order 1 over square root of n, and very rapid fluctuations. So this is a sketch, it's not a simulation. And then once the drop or the crystal is formed, you have a Brownian particle, which has much bigger fluctuations because now the particle can explore the whole box, so the fluctuations are the whole box, but they are much slower. So you have created a huge separation between time scales from here to here. So, and you have created the macroscopic degree of freedom. We go back to this idea. I started the video saying that I want to get rid of macro, micro, but it's true that we have macroscopic degrees of freedom. And if I try to see how these macroscopic degrees of freedoms are generated, I think that the mechanism should be a continuous symmetry breaking. When we say the position of this pen is here, is because there is a symmetry breaking. The position, the pen can be anywhere, and this is because symmetry is broken. And this also, I think, it has consequences on what we understand by information, because information from some point of view needs the separation, a huge separation between time scales. When you have an information device, the information device must store information in a reliable way, so it must have states with very long lifetime and stable for a long time. So this means that there must be a huge separation between time scales. But these are very speculative ideas and suggestions for those interested in these fundamental problems. So this is all. Thank you very much. Please comment, because I will be happy to see what people think about these ideas. And thank you very much.